Hello and welcome back to my stream. Today we're going to be working on Philipp Oppermann's blog of writing an OS in Rust. We're up to the Async Await chapter, which is the last blog entry that he made for this project. So this is going to be the last section that we're going to do. There's a lot more work to do to make a real operating system, as I've explained before. We still need processes and a scheduler. We still need to be able to do the syscall interface, and we still need all the other features that an operating system provides, access to other parts of the hardware, like we have memory done, but we need, like, at a minimum, networking and a file system. So those are still missing, and I'm not sure if there's any plans to add those, because this last one was done on March 27th of 2020, which is over 2 years ago now. Although the GitHub is still actively maintained. Let's take a quick peek over there, just to take a look at it. And there's PRs, there's issues, and it's pretty active. 8 days ago was the last commit. So fingers crossed. I mean, I'm going to email him and find out what he thinks the next thing would be to do, and we could try to do it on our own. I'm not sure, writing a scheduler would be good if we don't have processes, but you can't really create processes if you don't have a scheduler. So I don't know. But we're going to dive in with Async Await and learn all about how multitasking works and take it from there. So, Async Await. In this post, we explore cooperative multitasking and the Async Await feature of Rust. We take a detailed look how Async Await works in Rust, including the design of the future trait, the state machine transformation, and pinning. We then add basic support for Async Await to our kernel by creating an asynchronous keyboard task and a basic executor. All right. Multitasking. One of the fundamental features of most operating systems is multitasking, which is the ability to execute multiple tasks concurrently. For example, you probably have other programs open while looking at this post, such as a text editor or terminal window. Even if you only have a single browser window open, there are probably various background tasks for managing your desktop windows, checking for updates, or indexing files. While it seems like all tasks run in parallel, only a single task can be executed on a CPU core at a time. To create the illusion that the tasks run in parallel, the operating system rapidly switches between active tasks so that each one can make a bit of progress. Since computers are fast, we don't notice these switches most of the time. While single-core CPUs can only execute a single task at a time, multi-core CPUs can run multiple tasks in a truly parallel way. For example, a CPU with 8 cores can run 8 tasks at the same time. We will explain how to set up multi-core CPUs in a future post. This is why I think there's still more to come. For this post, we will focus on single-core CPUs for simplicity. It's worth noting that all multi-core CPUs start with only a single active core, so we can treat them as single-core CPUs for now. There are 2 forms of multitasking. Cooperative multitasking requires tasks to regularly give up control of the CPU so that other tasks can make progress. And preemptive multitasking uses operating system functionality to switch threads at arbitrary points in time by forcibly pausing them. In the following, we will explore the 2 forms of multitasking in more detail and discuss the respective advantages and drawbacks. Preemptive multitasking. The idea behind preemptive multitasking is that the operating system controls when to switch tasks. For that, it utilizes the fact that it regains control of the CPU on each interrupt. This makes it possible to switch tasks whenever new input is available to the system. For example, it would be possible to switch tasks when the mouse is moved or a network packet arrives. The operating system can also determine the exact time that the task is allowed to run by configuring a hardware timer to send an interrupt after that time. Yeah, and we actually have a hardware. If I say cargo run right now, we'll see dots coming out. And the reason we see the dots coming out is because we set up a hardware timer interrupt handler that prints a dot to the screen. And so it's happening like 10 times a second or something like that. The following graphic illustrates the task switching process on a hardware interrupt. Task A1 is executing. Okay, CPU is running task A. Hardware interrupt occurs, interrupt handler executing. So the operating system is now running the interrupt handler on the CPU before it was running task A1. Interrupt handler switched to task B. So now it's running task B1. In the first row, the CPU is executing task A1 of program A. All other tasks are paused. In the second row, a hardware interrupt arrives at the CPU. As described in the hardware interrupts post, the CPU immediately stops the execution of task A1 and jumps to the interrupt handler defined in the interrupt descriptor table. Through this interrupt handler, the operating system now has control of the CPU again, which allows it to switch to task B1 instead of continuing task A1. Right, but it has to save all of the state that A1 had so that when we resume A1 in some future time, we're going to be able to come back to it. Right, okay, so saving state. Since tasks are interrupted at arbitrary points in time, they might be in the middle of some calculations. In order to be able to resume them later, the operating system must back up the whole state of the task, including its call stack and the values of all CPU registers. This process is called a context switch. As the call stack can be very large, the operating system typically sets up a separate call stack for each task instead of backing up the call stack content on each task switch. Such a task with a separate stack is called a thread of execution, or a thread for short. By using a separate stack for each task, only the register contents need to be saved on a context switch, including the program counter and stack pointer. This approach minimizes the performance overhead of a context switch, which is very important since the context switches often occur up to 100 times per second. The main disadvantage of preemptive multitasking is the operating system can fully control the allowed execution time of a task. Oh, that's the main advantage, not disadvantage. Sorry. The main advantage of preemptive multitasking is that the operating system can fully control the allowed execution time of a task. This way, it can guarantee that each task gets a fair share of the CPU time without the need to trust the tasks to cooperate. This is especially important when running third-party tasks or when multiple users share a system. The disadvantage of preemption is that each task requires its own stack. Compared to shared stack, this results in higher memory usage per task and often limits the number of tasks in the system. Another disadvantage is that the operating system always has to save the complete CPU register state on each task switch, even if the task is only used a small subset of the registers. Okay, yeah, that makes sense, because there's no way for the OS to know which registers the tasks used. Preemptive multitasking and threads are fundamental concepts of an operating system because they make it possible to run untrusted user space programs. We will discuss these concepts in full detail in future posts. For this post, however, we will focus on cooperative multitasking, which also provides useful capabilities for our kernel. Cooperative multitasking. Instead of forcibly pausing running tasks at arbitrary points in time, cooperative multitasking lets each task run until it voluntarily gives up control of the CPU. This allows tasks to pause themselves at convenient points in time, for example, when it needs to wait for an I/O operation anyway. Cooperative multitasking is often used at the language level, for example, in the form of coroutines or async await. The idea is that either the programmer or the compiler inserts yield operations into the program, which give up control of the CPU and allow other tasks to run. For example, a yield could be inserted after each iteration of a complex loop. Star Wars Chess, thank you for the follow. It's common to combine cooperative multitasking with asynchronous operations. Instead of waiting until an operation is finished and preventing other tasks to run in this time, asynchronous operations return a not ready status if the operation is not yet finished. In this case, the waiting task can execute a yield operation to let other tasks run. Saving state. Since tasks define their pause points themselves, they don't need the operating system to save their state. Instead, they can save exactly the state they need for continuation before they pause themselves, which often results in better performance. For example, a task that just finished a complex computation might only need to back up the final result of the computation, since it does not need the intermediate results anymore. Language-supported implementations of cooperative tasks are often even able to back up the required parts of the call stack before pausing. As an example, Rust's Async Await implementation stores all local variables that are still needed in an automatically generated struct. By backing up the relevant parts of the call stack before pausing, all tasks can share a single call stack, which results in much smaller memory consumption per task. This makes it possible to create an almost arbitrary number of cooperative tasks without running out of memory. The drawback of cooperative multitasking is that an uncooperative task can potentially run for an unlimited amount of time. Thus, a malicious or buggy task can prevent other tasks from running and slow down or even block the whole system. For this reason, cooperative multitasking should only be used when all tasks are known to cooperate. As a counterexample, it's not a good idea to make the operating system rely on the cooperation of arbitrary user-level programs. However, the strong performance and memory benefits of cooperative multitasking make it a good approach for usage within a program, especially in combination with asynchronous operations. Since an operating system kernel is a performance-critical program that interacts with asynchronous hardware, cooperative multitasking seems like a good approach for implementing concurrency. Okay. Async Await in Rust. The Rust language provides first-class support for cooperative multitasking in the form of Async Await. Before we can explore what Async Await is and how it works, we need to understand how futures and asynchronous programming work in Rust. Futures. A future represents a value that might not be available yet. This could be, for example, an integer that is computed by another task or file that is downloaded from the network. Instead of waiting until the value is available, futures make it possible to continue execution until the value is needed. Example, the concept of futures is best illustrated with a small example. We have a read file, we return file, we call foo, we return from foo, we have async, read file, return a future, the file is available, we call foo. Oh, I see, the file is available here, but we can call foo and return while we're waiting for the file to become available. That makes sense. This sequence diagram shows a main function that reads a file from the file system and then calls the function foo. This process is repeated 2 times, once with an asynchronous read file call and once with a synchronous read file call and once with an asynchronous async read file call. When the synchronous call, the main function needs to wait until the file is loaded from the file system. Only then it can call the foo function, which requires it to again wait for the result. With the asynchronous async read file call, the file system directly returns a future and loads the file asynchronously in the background. This allows the main function to call foo much earlier, which then runs in parallel with the file load. In this example, the file load even finishes before foo returns, so main can directly work with the file without further waiting after foo returns. Futures in Rust. In Rust, futures are represented by the future trait, which looks like this. Trait future, we have a type output, and we have a poll function, which returns a self-output type. The associated type outputs specify the type of the asynchronous value. For example, the async read file function in the diagram above would return a future instance with output set to file. The poll method allows to check if the value is already available. It returns a poll enum, which looks like this, ready or pending. When the value is already available, e.g. the file was fully read from disk, it is returned wrapped in the ready variant. Otherwise, the pending variant is returned, which signals the caller that the value is not yet available. The poll method takes 2 arguments, self, pin mute self, and cx mute context. The former behaves like a normal mute self reference, with the difference that the self value is pinned to its memory location. Understanding pin and why it's needed is difficult without understanding how async await works first. We will therefore explain it later in this post. The purpose of the cxmute context parameter is to pass a waker instance to the asynchronous task, e.g. the file system load. The waker allows the asynchronous task to signal that it or a part of it is finished, e.g. that the file was loaded from disk. Since the main task knows that it will be notified when the future is ready, it does not need to call poll over and over again. We'll explain this process in more detail later in this post when we implement our own waker type. Working with futures. We now know how futures are defined and understand the basic idea behind the poll method. However, we still don't know how to effectively work with futures. The problem is that futures represent values of asynchronous tasks, which might not be available yet. In practice, however, we often need these values directly for further calculations, so the question is, how can we efficiently retrieve the value of a future when we need it? Waiting on futures. One possible answer is to wait until a future becomes ready. This could look something like this. A future equals async read file. Let file content is loop. Match future poll. Ready, pending. Okay, so this is just blocking in a loop, which defeats the whole point, right? Here we actively wait for the future by calling poll over and over again in the loop. The arguments to poll don't matter here, so we omitted them. While this solution works, it's very inefficient because we keep the CPU busy until the value becomes available. Mafanya Tapayu. Sorry, I don't know how to pronounce that, but thank you for the follow. A more efficient approach could be to block the current thread until a future becomes available. This is, of course, only possible if you have threads, so this solution does not work for our kernel, at least not yet. Even on systems where blocking is supported, it is often not desired because it turns an asynchronous task into a synchronous task again, thereby inhibiting the potential performance benefit of parallel tasks. Yeah. Future combinators. An alternative to waiting is to use future combinators. Future combinators are methods like map that allow chaining and combining futures together, similar to the methods on iterator. Instead of waiting on the future, these combinators return a future themselves, which applies mapping operation on poll. Interesting. As an example, a simple string-len combinator for converting a future output equals string to a future output equals usize could look like this. So we have a string-len with an inner future f. We implement future for string-len, and the output is usize. Self inner future poll. So we're polling to see when the string is ready, and then we're going to return a len, a poll ready len. If the inner future is pending, then we're going to return pending. And then here's string len, which takes something that implements a future with a associated type of string, and outputs a future, outputs something that implements a future with an associated type of usize. And this is just creating it. Okay, and then it says file len implement future usize. File content future is async read file. So file content future must be the future, and then we call string len on it. And that returns the length of the string after polling for the file to be ready. Okay. This code does not quite work because it does not handle pinning, but it suffices as an example. The basic idea is that the string-len function wraps a given future instance into a new string-len struct, that's up here, which also implements a future. When the wrapped future is polled, it polls the inner future, that's right here. If the value is not ready yet, poll pending is returned from the wrapped future too. If the value is ready, the string is extracted from poll ready, right there. And its length is calculated, right there. Afterwards, it's wrapped in a poll ready, and again returned. With this string-len function, we can calculate the length of an asynchronous string without waiting for it. Since the function returns a future again, the caller can't work directly on the returned value, but needs to use a combinator of functions again. This way, the whole call graph becomes asynchronous, and we can efficiently wait for multiple futures at once at some point, e.g. in the main function. Manually writing combinator functions is difficult, therefore they are often provided by libraries. While Rust's standard library itself provides no combinator methods yet, the semi-official and no standard compatible futures crate does. Let's take a quick peek there. This crate provides a number of core abstractions for writing asynchronous code, futures, streams, syncs, and executors. Also contains abstractions for async I/O and crosstalk communication. Okay. Its future ext trait provides high-level combinator methods such as map or then, which can be used to manipulate the result with arbitrary closures. Advantages. The big advantage of future combinators is that they keep the operations asynchronous. In combination with asynchronous I/O interfaces, this approach can lead to very high performance. The fact that future combinators are implemented as normal structs with trait implementations allows the compiler to excessively optimize them. Maybe excessive is not the right word there, but I think I understand what he's going for. For more details, see the zero-cost futures in Rust post, which announced the addition of futures to the Rust ecosystem. Drawbacks. While future combinators make it possible to write very efficient code, they can be difficult to use in some situations because of the type system and the closure-based interface. For example, consider the code like this. All right, so here I have an example which takes a min-len and it outputs something that implements a future with a string as associated type. Do an async read file, then move content. If content len is less than minimum len, then we have this either thing, either left or right. Async read file bar text or future ready content. Okay. Here we read the file foo text and then use the then combinator to chain a second future based on the file content. If the content length is smaller than the given min-len, we read a different bar text file and append it to the content using the map combinator. Otherwise, we return only the content of foo.text. We need to use the move keyword for the closure pass to then because otherwise there would be a lifetime error for min-len. The reason for the either wrapper is that if and else blocks must always have the same type. Since we return different future types in the blocks, we must use a wrapper type to unify them into a single type. Okay, does either come from here as well? I don't know where either comes from. There is a link here to try it in the playground, so maybe there's a little more detail here. Oops. Yeah, so it comes from the futures crate, either. I was looking over here to see if I could see structs, but I don't see all the structs. So we can look up either. Yeah. And it just has left and right with different types. Each one can be its own type. But it combines it into a single type, which is nice. Okay. Right. Okay, since we return different future types, right, we must use the wrapper type to unify them into a single type. The ready function wraps a value into a future, which is immediately ready. That's this here. The function is required here because the either wrapper expects the wrapped value implements future. So this has to be something that implements future. Does it say that somewhere? I don't see it here. Or maybe, oh, no, it doesn't say that. So I'm not sure what they mean. That it's expecting it to implement future, because I don't see it implementing future here. I don't know. Okay. So that's something for me to investigate. As you can imagine, this can quickly lead to very complex code for larger projects. It gets especially complicated if borrowing and different lifetimes are involved. For this reason, a lot of work was invested to add support for Async Await to Rust, with the goal of making asynchronous code radically simpler to write.